Welcome back, ladies and gentlemen. In this video, we are looking at this idea of action or reaction, and I know you've heard this one before. Everyone has sort of done this sort of sing-song version of Newton's third law, and that's essentially what we're talking about, where you say, well, for every action, there's an equal reaction, or even better, for every action, there's an equal but opposite reaction. Okay, great. Easy to remember. You've been hearing that for years, I bet. But there's actually a lot more to this law. This is Newton's third law of motion. We've seen the law of inertia. That's his first law. We've seen F equals ma. That's the second law. And now we see the third law. You can call it action or reaction. For short, I just like to say third law. And something... We'll get to something that helps me remember that. You might find that helps you remember this as well, but otherwise it's pretty easy all on its own. So why is this important? Okay, all kinds of cool stuff. Lions, tigers, and bears. Satellites, cars, butterflies, submarines, airplanes, skateboards, shopping carts, and rockets. Oh my. So, everything. Literally everything. I'm not kidding. Everything. Will be sort of an example or is a thing or a place you can apply Newton's third law to. Once you understand this and dive into it, it's pretty easy, pretty straightforward, but you'll see, there's some things you may not have realized yet. And it's really cool. So here it is. Here is Newton's third law. There's three parts to it. Third law, three parts. That's the way I like to try to remember this stuff. So first part, forces come in pairs. Always. Always. There is never a single force out there. Another way of looking at this, though, if that weirds you out, then you can think of as a force is a thing that affects two different objects, not just one. But I prefer to think of it as two forces. They're pairs, and actually they're sort of twins. Forces in a pair act on different objects. Forgive my lack of a little bit of whiteout right there. So these two forces, they act on different objects, and what that means, that's real important. That means that these two forces cannot ever cancel each other out because they're acting on different objects. They do not ever cancel out. They can be canceled by other forces, but the two forces in a pair will never cancel each other out, ever, ever, ever. Remember that. And finally, forces in a pair act in opposite directions. Okay, so that's really important, but it's pretty darn easy. So here's our situation. You are standing on Earth. Maybe that's kind of uncommon for you. You don't like to hang out here on Earth too much. I don't know, but here you are. So free body diagram of you. We have Earth's gravitational force pulling you down. There is a normal force pulling you or pushing you up, and they are equal. So they cancel out. You are in a state of, starts with the E. You know what it is. But what about the forces acting on Earth in this situation? So we have a free body diagram of the Earth. This is interesting. There's a gravitational force pulling the Earth up. This gravitational force is part of a pair. It's here acting on you, and it's here acting on the Earth. And look at this. So there's a pair. They're twinsies. They act on different objects. This one is acting on you, and this one is acting on the Earth. And they act in opposite directions. This one's pulling down, that one is pulling up. And it's exactly true. Earth is pulling you down with a certain amount of force. You are pulling Earth up with the exact same amount of force. No one ever thinks of it like that. Earth doesn't, if Earth could notice something, Earth doesn't notice this force. But it's true. The old joke, okay, when Chuck Norris does push-ups, he's not pushing himself up, he's pushing the Earth down. It's true! And when you do push-ups, it's true! So there's a normal force. Earth is pushing you up. Well, there's a force that you create acting on the Earth, pushing the Earth down. It's true! And those two are twinsies. They are a force pair. They're equal, they act on different objects, and they act in opposite directions. So look at this. I mean, you're in a state of equilibrium as you stand there, and Earth is in a state of equilibrium in this particular super simplified situation. So everything They do cancel out. But notice that this is not canceled by its twin. It's canceled by a completely different force. That's real important. All right. So one of the things that makes this law really cool and kind of fun, that teaches you how you can launch a rocket, how rockets work. So you want to launch a rocket, you have to accelerate that rocket upward. You do that by creating an unbalanced force. Okay, you want the rocket to accelerate, there must be an unbalanced force acting on it. Awesome. I'm going to launch the rocket upward. Here's free body diagram of the rocket. We want that acceleration in the positive y direction. Brilliant. We need this upward force, and I'm just going to call it force of thrust. We need to create that force acting on the rocket. How do we do that? Forces must come in pairs. So in order to create this force, we have to create an equal but opposite force acting on something else. What is that something else? It turns out that something else is the exhaust gases coming out of the back of the engine. Those molecules are the something else. Those molecules are shot out the back of the engine of the rocket. They are absolutely necessary. And the way rockets work, they carry those inside. That's part of the fuel, and the fuel gets burned or consumed or whatever kind of style engine it is. Those molecules must be sort of shot out the back of the rocket. Then they have a force applied to them. It's a force of thrust in the opposite direction. Those exhaust gases accelerate in the negative y direction in this situation. So we end up with the rocket accelerating upward in this situation, and the hot exhaust gases accelerating downward in the same situation here. These two forces are part of a force pair. They are equal. They act on opposite object or different objects, and they act in opposite directions. So here's what you might envision this rocket flying through space. It doesn't matter how it's rotated, how it's oriented. That's not the important thing, not at all. What's important is that the rocket experiences this force of thrust in that direction, and that's what we wanted. We don't care about this stuff happening at the back, but the stuff happening at the back is necessary. Because to create this force forward, we have to create that force backward. It's non-negotiable. The universe doesn't let us do one without the other. So the rocket has to carry those molecules with it and shoot them out the back. Now if you recall Newton's second law, F equals ma, or acceleration is equal to net force divided by the mass. Notice the mass difference here. Each of those molecules is really infinitesimal in mass compared to the mass of the rocket. I mean, they're super tiny compared to that mass. They experience the same force, though. That's what Newton's third law says. So what do you suppose is going to happen here? Does the rocket experience a larger acceleration, or do the exhaust gas molecules experience a larger acceleration? Remember, the same force, and there's much less mass here. So you apply Newton's second law to figure that out. I'll leave this to you to figure out which one would experience a greater acceleration, the rocket or the exhaust. And that is Newton's third law. Thanks for watching. I'll catch you next time.